All right, guys, here we're going to be talking about all the computational things you can be doing with vectors here. So, a vector in standard position in the rectangular coordinate system can be uniquely described by the coordinates of its terminal point. The notation used for vectors in standard position is going to look like this right here, where you have these little brackets and then you put your x distance and then your y distance that it travels here. This is called component form of a vector, and we're going to use that quite a bit throughout the lesson here. To find the component form of a vector that is not in standard position, you can use the coordinates of its initial and terminal points. So we're going to start out with an initial point and a terminal point here, and then we're going to convert that here into this component form in just a second. The process of doing that here is essentially you're going to take your two x's from your two different vectors and your two y's from your two different vectors, and essentially you're just going to subtract them. We learned back in geometry that to find the distance between 2 points, especially like on a number line, you would just subtract. So we're going to kind of keep that same theme going here. All right, the magnitude, we talked a little bit about that in the last lesson. The magnitude is, how long the vector is going to be. It's the quantity that is involved with that. And basically, it's in a way tied to your distance formula. The distance formula, you take your differences of your x's, and you get that, and then you square it, and you get the distances between your y's. You square those as well, and then you square root both sides there at the end. So essentially it's kind of like distance formula. So we're going to now go find the component form here of this vector. So one thing you might also want to always write down here, it's always going to be the terminal point. That's going to be the finishing point. And then you're going to subtract the initial. Okay. The order of the subtraction definitely matters because you might have the wrong direction if you subtract them out of order. So with that being said, sorry, got a pop-up showing up. Okay, with that being said here, we'll go and take our two x's right there. So you'll do 3 and then minus -4. That's going to be your x component. And then your y component, you're going to do the -5. And then I guess you're going to take away the 2. And just don't, forget about your normal arithmetic things here. Minus a negative is like addition. So 3 plus 4 is going to be 7, -5, and then take away 2 more will be -7 there. So your component form will look like this here. It'll be the x part first, 7, and then the second part right there, -7. And what that means right there is go right 7 and then down 7 based off of that. All right, now to take that and find the magnitude, you're going to go and take this component form right here. You're going to do the square root of this, and then you're going to do +7 squared, and then you're going to add on -7 squared. And if you're using your calculator to type that in, make sure you put the extra set of parentheses around that. -7 there, because a lot of people forget the parentheses, and then the calculator thinks you're squaring the 7 and then making it negative. I typically will just do this though in my head, or at least like kind of do everything like individually, step by step. Because a lot of times we're going to need radical form, so the calculator's not going to be able to help us out too much there for that. All right, we're going to get 98 when we simplify, and then we can break that down. That's 49 times 2, and then 7 and 7. So simple is radical form, which is how you're going to leave most of your answers. It's going to look like that, 7 square root of 2. So that is the magnitude of that vector in component form. Okay. Now coming up here, you can do a lot of different things with vectors when they're in component form. We'll apply this a little bit in the lesson tomorrow, but for these first few here, we're just going to add and subtract and maybe scale them a little bit here. So first one here, we're going to do the vector w plus the vector y. And, I guess here's how I would write it out. You do 4, 1 right there, and then you're going to add on the 2, 5. And basically you just add your two x's together and you add your two y's together because of this right here. So this is where you're kind of doing things with multiple vectors. So you're going backwards, 4, but then 4 or 2. If you add those up, that comes out to -2 essentially. You're just adding, that's all. Here you got 1 and then 5. You combine those up, that'll come out to 6 right there. So -2, 6 is a result of adding those vectors. can also subtract them. Coming up here with b, it looks like you got subtraction, and you're going to scale the y vector by 2. So I would write it like this here. Here's your z. It's negative 3, 0. Then I'm going to go minus and then 2. And I'll put that outside of the y vector, which was 2 and 5. And then I would almost treat this kind of like a distributive property. I know they're not parentheses, so it's quite the same, but I mean, essentially it is. That'll be negative 4 and then negative 10. And then you can put a plus here in between them. And drop down that negative 3, 0. And then that comes out to negative 7 when you combine them up. And then negative 10. And by the way, I kind of glossed over this, or kind of quickly went over this here. I changed that to plus right there since I distributed the negative. You no longer have a negative there, so it changes to addition. Okay, so that'll be it there on those. Two more that are pretty similar here. You got 4w. So here I have it written down here in my notes. W was negative 4 and then 1. And then the z1 was negative 3 and 0. So this would be what, negative 16 and 4. And then you're going to add the negative 3 and 0 to those. So what was that, negative 19 and then positive 4. So that's your final answer there on those. And then the final one here, you got 3 vectors going on. 2 times w, 4 times y, and then subtract off z. Okay, so got it off screen here, but my notes say we got negative 4, 1 there for w. And then we got the 2 on the outside, and we got 4, and then the y1 was 2, 5. And then minus the z. All right, so let's see here. This becomes, let's see here, negative 8, and then 2. Next one will be, what is that, 8, 20. And then I'm going to go ahead and distribute the negative part here and change this to addition, so I don't have to do as much thinking, and that would become positive 3, 0. And then just combine them up. Negative 8 and then plus 8 cancels, and add 3 to that. You should have 3. Got 2 and then 20. Come out to 22. So pretty straightforward there on those. Nothing too bad on those. You just add them up. Okay, now this next thing here, we're going to talk about unit vectors. A unit vector is a vector specifically with a magnitude of 1 right there. Okay, so there is a way to go and take normal vectors and then get them to where the magnitudes are truly 1. And you're going to do this little process here. So I like to look at this here. So this is going to be your vector in component form. And then I think we showed you guys yesterday, but in case you forgot, when you have these little bars there around a vector, that notation is talking about the magnitude of the vector. So we're going to have to find the magnitude kind of like how we did in the first section. And then we're going to take both vector pieces and then we're going to divide them by the magnitude. And that'll get us to where we have a vector truly with a magnitude of 1 right there. So we're going to go ahead and try it out here on this next one here. Find a unit vector with the same direction as this vector right here. So essentially what does that mean? That means first of all I need to find the magnitude, which is, so the magnitude is, looks like this. And we just do, that's where you do the square roots, basically your distance formula. Negative 2 squared and then 3 squared. It's going to come out to 4. And then what is that, 9 right there? That's going to come out to root 13. Okay, and I'm going to leave it like that. A lot of times we'll leave these in radical form if possible. I guess you could do decimal form if you want to get real fancy. And then after you do that, the whole thing said take your vector and then divide it by the magnitude of your vector, which means take your vector negative 2 and 3, and then you're going to divide both of those by the magnitude of root 13. You'll just write those out individually, kind of like that. And then you can go ahead and rationalize where you multiply top and bottom by square root of 13. That'll come out to negative 2 square root of 13 over regular 13. And then 3 root 13, and then over 13 like that right there. And now if you actually happen to go back and do your magnitude process like we just did up here, if you do that with these, theoretically it should come out to 1. It should simplify there real nice. So that'll be that process there. We only have one example on that, but you'll see those unit vector problems quite a few times there. So also too want to point out all the signs kind of still match up, and that's because it still needs to go in that same direction. We just manipulated it to where it has a magnitude of 1. Okay. This next part here, we're going to talk about linear combinations. So the unit vectors in the direction of the positive x-axis and y-axis are denoted by, we can call I this unit vector here of 1, 0, and then j 0, 1 right there. The vectors I and j are called standard unit vectors. And if we go and combine them up here, these vectors can be used to express any vector in component form, and we can write it as, whatever a is, whatever that number is, times I, and then whatever that b number is, you can do that times j. And the sum of these here is called a linear combination. Now, essentially, to boil it down here, it's really just a different format of your component form, but it's really not anything drastically different here. So what we're going to do here on these next examples is we're going to write it as a linear combination, these two vectors here with the initial and terminal points. We're going to write it as a linear combination. What I'm going to do first, though, is get it in component form. And then after that, we'll do the linear combination. And you're going to kind of just see that these wind up being the same thing. They're not drastically different here. So the component form here, you're just going to subtract. I need 4 minus negative 2. And then you need 5 minus 3. So this will come out to 6 and 2 right there. So your component form will just be 6 and then 2. And then the linear combination format here, you just write 6i and then plus 2 and then j. That's your linear combinations. Different format. I see sometimes you'll see those in physics classes, sometimes maybe the college physics classes. But that's, essentially it there. It's really not too bad. Let's try out another one here. Your linear combination for this one here, well, first of all, let's get component form. 2 minus negative 6 would be 8. And then 5 minus 0 would be 5. So then that would be 8i and then plus 5 times j. There's your linear combination form. So not a whole lot to memorize there about that, and just you need to know that they're the same. Okay, let's try this last one here. Component form, negative 7, and then take away 3 more. That'd be negative 10, I think. Or actually, I'm sorry. No, that'd be negative 7. I'm messing up some arithmetic. Minus negative 3, that would be adding. So negative 4, and then 1 minus negative 8 there, that would be adding. That would be 9. And then negative 4i plus 9j, and that would be it. So pretty straightforward on those there. Nothing too much to memorize. All right, let's see what else we got here. Next, ways to specify the direction of a vector. AB right there is to state the direction angle theta that makes the vector v makes with the positive x-axis. It follows that v can be written in component form or as a linear combination of I and j using the magnitude and the direction angle of the vector. So this is basically taking a vector, like if I give you like down here, where is it? Oh yeah, like right here, I'm going to have a magnitude of 10 and then 120 degrees. So if I have those two things, the angle and then the magnitude of it, you can use this idea up here and convert it into component form. And that's essentially what we're about to do here on this. I'll read this next part here in just a second and tie it back to that. But let's try this out here. Write the component form of a vector at the magnitude of 10 and a direction angle of 120. So essentially, like what you're going to do is you normally will have these triangles, and then you can say, hey, like if I go and do my opposite, adjacent, and hypotenuse and do some trigonometry, you wind up finding that your vector times sine of whatever your angle is, that's going to get you the vertical part. And then your vector times your cosine part right here, and then that's going to get you the x piece, and then you put those together as your component form, essentially. Now, what's a little bit different here about this is sometimes we'll give you angles, bigger than 100 or bigger than 90 degrees, so it might not be in that top quadrant. So like on this one here, if you're to sketch it out, a vector with an angle of 120 degrees, usually if they don't say anything, they're assuming from the positive x-axis. That'd be somewhere over here. So there's your start and end points there, and it's got a magnitude of 10. Put that right here, and then 120 degrees, kind of like that. So you could go and like kind of set up like a right triangle if you want, but we have these little formulas here, and it's pretty simple. It's just your magnitude times cosine, that gets you the x piece, and then your magnitude times your sine right there, that'll get you your y. So cosine kind of goes with x, sine goes with y, just like your unit circles there. So let's go ahead and write it out here. So let's try this out. So it'll be 10, and then I guess for the x piece, that'll be cosine. 10 times cosine, and then of 120 degrees right there. And then you can also do this for the x, by the way. For the y's, it'd be 10, and then times sine of 120 degrees. Now, you could type those into the calculator. I think a lot of times, though, we're going to ask you guys these for radical form. So what you're going to need to do is use the unit circle and actually go and figure out cosine of 120 degrees. So, I got that written down off screen here. The cosine of 120, if you go find that on your unit circle, that should come out to negative half. So 10 times negative half will actually come out to negative 5. Over here for sine of 120, sine of 120 is actually the root 3, and then over 2. And then you could do the 10 divided by 2 right there. It'll come out to 5. So this will come out to 5 root 3. And then just put it together as your component form. You go negative 5 and then comma 5 root 3. And that'll get you your vector right there in component form. And that'll actually help us with some of the word problems that we looked at. I think that we started some of those in 8.1. We can use this whole idea of splitting it up and do it, magnitude times cosine and magnitude times sine to make it to where you get component form. It makes it easier to add your vectors up there. So that's kind of the big idea there on that. Now the section down here below is going to be kind of tied to the angle. So we're going to do tangent of those here. It also follows that the direction angle theta of a vector can be found by solving the trig equation right there. So like tangent's typically like your opposite over your adjacent sides, and the opposite's going to be the sine of theta, and then the cosine's going to be cosine will be the adjacent side right there. So it essentially turns out to where you just put your b value over your a. But honestly, on these, I just kind of sketch it out, honestly. Let me show you kind of what I'm talking about here. On this one right here, we're going to do the vector. So it's going to go basically right 3 and up 7. So that's your vector going right 3, up 7. Maybe I'll make it a little bit more steep here just to kind of make it somewhat to scale. Okay, so there's your vector right there. Go ahead and make it into a right triangle, and then put your 3 and 7. And usually they're going to just ask you, hey, what's the angle? And honestly, I just use regular, trigonometry that we've learned from geometry there to find it. We just say, hey, tangent of theta equals 7 over 3. And then don't forget, when you're solving for an angle there, you do tangent inverse of both sides to cancel out. And then we need to do tangent inverse of 7 divided by 3, kind of like that. So let's see if we can do that second tangent. Make sure your calculator is in degree mode so we can get the actual number of degrees. So we'll say theta is about 66.8 or 67 degrees if you round to the nearest whole number. They said to the nearest tenth, so let's go 66.8. And that'll be it right there. So pretty straightforward. The only thing that starts getting weird with these is when you start messing around with the different quadrants because of the way tangent inverse works. Tangent inverse, back from chapter 4, we said usually those input values, you'd want to do anything in the top right quadrant or quadrant 1 or quadrant 4. So when you start getting outside of those quadrants, things kind of get a little weird, and we might need to use some logic to help ourselves out with those. B is going to be in the bottom right quadrant, so tangent inverse should work just as intended here on this. So let's sketch it out here. We're going to go right 4 and then down 5 right there. We're going to find theta again. So we'll do tangent inverse of essentially -5/4. That's skipping a step or two right there. If you want to write the full thing, I guess you could do tangent theta. It's -5/4, but then you tangent inverse both sides. And you can actually input that into the calculator and get something that does come out pretty good here. You can even type it with the negative. If you type it with the negative, it will give you that theta is -51.3 right there, which means you're going down -51 degrees right there. So you can leave it like that right there, or I guess you could add 360 to it if you want to get the full rotation right there. So yeah, just 360 plus your answer. I guess you could say 308.7 degrees right there. Normally -51 I think should be sufficient right there, but either of those should work right there. And kind of like what I was saying here, when you start doing different quadrants that aren't typically where tangent inverse happens, we got to be a little bit careful here with these. So like example here, I think this one here is in the top left quadrant. So when you sketch it out here and do your triangle, it's backwards 6 and then up 2. All right, now if you do tangent inverse with those, you're going to get a negative angle. So you almost I guess when they're in different quadrants, it might be a good idea to actually just go and sketch it out here with the positive versions. Find your angle and then somehow tie that back to like how many degrees you're rotating from the x-axis. That's probably the way I would approach it. So here's what I'm going to do. I'm going to set it up down here using the positive versions here. So tangent inverse of 2/6. And that comes out to about 18.4 degrees. So that means this angle here, 18.4 degrees right there. So if you think about it, use logic here to find this angle on the outside right here. You're going to do, or use the idea that makes a straight line there. And you can just go 180 minus the 18.4 degrees. And that comes out to 161.6 degrees right there. So that's probably how I would do that right there. If you go, and just let me show you here, if you do second tangent and then do 2 divided by -6, it's going to give you -18.4, but then that kind of doesn't make sense when we go back and look at our original triangle there, and that's because tangent inverse typically doesn't exist there. So it gets a little weird on those ones in the different quadrants, so be a little careful on that. Okay, this last one, kind of the same idea. Tangent inverse is not going to exist in this bottom left quadrant or quadrant 3. So it should look something kind of like this here. Theta, -3, -8. So same idea. I'm just going to make the right triangle again, do the positive versions, and then use the logic from here. So let's see here. Second tangent, this would be 8 divided by 3. So that angle there, about 69.4. So if this angle is 69.4 right there, and you're trying to find how many degrees to this right here, instead of subtracting, doing 180 minus your angle, from here to here is 180, so you really just do 180 plus the 69.4 degrees. And that comes out to 249.4. And that will be the best thing to write there. So that is that on the angles. Got to be a little bit, careful, I guess, when sketching those in the quadrants outside of where tangent to inverse exist. Okay. All right, last section here, we're going to talk about the dot product. Now, I know there's a ton of different applications you can do with the dot product with vectors. The only one we're going to look at here is we're going to eventually find the angle between these two separate vectors. And that's actually pretty challenging here without the little formula. So we're going to use that, and it calls for this thing right here. That's notation right here. And let me. So with that, the dot product here, you'll go and take whatever your vector is, and you're going to do the two x pieces essentially. You're going to multiply those together. So you'll have some type of x times another x. And then you'll take your two y pieces right here, and you'll multiply those together. Okay, and then once you get those products, you add it up. Okay, so really this comes out to where each of your dot products is going to be a number typically. It's going to be, I think they sometimes say it'll be a scalar. So usually it'll just equal some type of, whole number essentially. So we're going to try it down here in a second. Notice that the dot product of two vectors is a scalar. It's not a vector. So scalar is just, a number. Two non-zero vectors are perpendicular, by the way, if and only if their dot product is 0. So if you have a dot product that comes out to 0, it means the vectors make a 90-degree angle or they're perpendicular. Two vectors with a dot product of 0, we have this vocabulary word here. It's orthogonal. It's actually spelled down there below. So that is only when the dot product comes out to be 0. So I think they'll ask you one or two questions there on that. So that's all you need to know. Is it 0 or not 0? So let's try it out here. Take your two x pieces and multiply them together. 3 times -4. And then you'll take your two y pieces, 6 and 2. And then you will add those together. And your dot product here is actually 0 right there. So since that happens, you can say that these were orthogonal. Next one here, dot product, two x's times each other right here. That'd be 2 times 8. And then plus, and then you got 5 and 4. And then, let's see here, that'd be 16 and 20. Add those up. Your dot product is 36. So this is not orthogonal. So if you were to actually draw them out, you wouldn't have a 90-degree angle between them. It's only when it's equal to 0. If you wanted to, you could sketch them out and do that. Okay, so next section here is kind of talking about, hey, if it's not 0, then we can find the angle here. And this will probably be, this has the most amount of steps that you're going to need to do from all the processes that we learned here today. The numerator right here, this is the dot product. I would even label it if I were you. And then right there, that's the magnitude of A. So you'll have two different vectors. That's the magnitude of your A vector. And then this right here is the magnitude of your B vector right there. So you're going to need to find your dot product, your magnitude of A, your magnitude of B, and then you can pop those into the formula. Now, you'll also have cosine of theta is equal to that. Most times you're actually trying to find theta, so after that, then you're going to do cosine inverse of both sides, which basically means type in cosine inverse, whatever that decimal is, and that'll get you your angle. A lot of times we'll round these as well to the nearest degree. So let's go ahead and try it out here. First thing I'm going to do is dot product. Your dot product here is going to be 6 and then times 4, and then plus 2 times 3. That's going to be 24 plus 6. That's going to come out to 30. Next, we're going to do a magnitude of your first vector, so magnitude of u. Okay, how do we do that? That's where you do the square root, 6 squared and 2 squared. So let's see here. That would be what square root would be 36 plus 4. That's going to be square root of 40. Now, y'all are going to be tempted to simplify that, but since our answer is going to come out to a decimal anyways, don't worry about breaking down that radical. It's going to be kind of a waste of time, honestly, because we're going to get an angle, and our angle most of the time is going to be a decimal anyways. All right, let's do magnitude of your second vector here. So the 4 squared and and the 3 squared. Actually, I think that comes out clean right there. That'd be square root of 25 after you add them up. Which will come out to exactly 5. Okay, so next we'll write it into our formula. It's going to be cosine of theta. It's going to equal your dot product, which we got to be 30. And then it's going to be the product of your two magnitudes, the 5 and then times the square root of 40. Okay. Now, if you are using the fraction button in the calculator, which is typically alpha y equals on this little app, I think it's just, I find it right there. Yeah, there's your fraction button. If you're typing in with the fraction button, just type it in the exact way it looks, and that'll be fine. If you're on a slightly older model for your calculator, it might not have that button. What you're going to need to do for this here is you're going to need to do cosine inverse, really, of both sides. Those are going to cancel, so you're going to get theta equals, and then it's going to be all of this. Basically, what you need to do is add in an extra set of parentheses to force the calculator to multiply the two denominators together first. So like as far as like what does that look like in the calculator, I'll hit second cosine for cosine inverse. You'll do 30 divided by, add an extra set of parentheses, and then you can do 5 times the square root of 40. And then make sure you get out of underneath your radical, close parentheses, close parentheses. If you type that in correctly, you should have gotten 18.4 degrees. And that'll be it right there. So on the older calculators, make sure you add the extra set of parentheses, and then that should keep you out of trouble. If you don't add that extra set of parentheses, you'll get something pretty drastically different, so you should be careful on that. All right, let's knock out this last one here. Same process, different numbers. Dot product here, let's see, that would be 3 times 3, and then plus 1 times negative 3. So that'd be 1 minus 3, essentially. That's going to come out to 6. Magnitude of u. That'd be 3 squared, and then 1 squared. Should come out to root 10. Magnitude of v. That'll be 3 squared. Ooh, make sure since this one's got the negative, you got to throw some parentheses around it if you're going to use your calculator to help simplify. Or you could just say, hey, that's 9 plus 9. Negative squared is positive, so it comes out to root 18. Then essentially from there, it's cosine inverse. And then it's going to be dot product, and then over the product of these two. If you want to be lazy and not have to worry about doing that extra set of parentheses, you could get fancy and go second cosine, and then 6 divided by, and then just say that's square root of 10 times square root of 18 is the same thing as the square root of 180. And that would eliminate the need for the extra set of parentheses. 63.4 degrees right there. And that should be it here for your 8, 2, and 3 lesson.